first examples studied by Poincaré and Klein. So example 1 actually was not studied by Poincaré, was not studied by Klein, was not studied by Schwarz. But they should have done it. I mentioned to you that if you take a polygon, and if you give me the angles, lambda 1 pi, lambda 2 pi, lambda n pi, where these lambda i's are between 0 and 1, and if you look for the conformal representation from the upper half plane to the polygon, I remind you that Schwarz was not convinced by the proof of the existence proof of Riemann, and he's proved that if there is such a map, then this map F has to be given by what we call the Schwarz-Christoffel formula, has to be of the form where the AIs, A1, A2, AN minus 1, are some real numbers. And I explained to you that in the case of a triangle, when you have only 3 vertices, choosing A1 and A2 is just invariant under homothesis, so you can always assume that A1 is 1, A1 is 0, and A2 is 1. So you have no choice to do for a triangle, and indeed, in the case of triangle, this gives an explicit formula for the conformal representation of the triangle. Now, what do you do if you have a quadrilateron? Well, for a quadrilateron, you have a fourth unknown. You are looking for A3. So you look for f of z is equal to the integral of dz, let's say z 1 minus lambda 1, 1 minus z 1 minus lambda 2, and then you have an unknown, which is A3, some real number. And your problem is, show that for at least one value of A3, you will indeed get the conformal representation of the given quadrilateron. So you are given the quadrilateron, and you want to show there is some AI, A3, which is such that this formula is correct. So this proof that is not in Schwarz, is not in Poincaré, is not in Klein, is nevertheless very simple to explain. What is clear is that if you choose A3, for any A3, let's say bigger than 1, this formula gives the representation of the upper half plane on some polygon. And this polygon has the right angles. Now, if you have you can choose C, and maybe I should add here a constant translation tau. And this is you can always assume, so 0, 1, A3, this is going to, you can assume that this side is going to 0, 1, say. This is going here. Now you know the angle. This is lambda 1. You know the angle. This is lambda 2. Maybe. Yeah. And then you have to complete the quadrilateron. What's the degree of freedom? Well, if you know that the angles of a quadrilateron, you know that you have only one degree of freedom because it's just have to choose this length. You can choose this length the way you want, and then you complete. Am I right or not? What is pentagon? Sorry. I know this angle. I know this angle. But I don't know this length. So the problem is to choose A3 such that this length L is the good one. So here's the trick. You look at the function A3 goes to the length of A3, which is given by this formula. It's the integral from let me choose correctly the one. Let me put this length, it's better. The integral from 1 to A3 of dz (1 minus z, 1 minus lambda 2, and A3 minus z, lambda 3. So everything is given. Lambda 1 is given, lambda 2 is given, lambda 3 is given, and A3 is the variable. Well, this is a function from 1 infinity to, let me take the modulus of this, or plus. And what you want to show is that for some A3, you have the correct value of the length. And the idea is very simple. Use the intermediate value theorem. So you will just show that this function is continuous, which is clear because it's given by a formula. And what you have to do is you have to understand what's happening when A3 is going to 1, and what's happening when A3 is going to infinity. In other words, in the Schwarz-Christoffel formula, you look at the behavior of this integral when A3 goes to 1 and when A3 goes to infinity, and you hope it will describe the full set of all possible quadrilaterons. And then if you can do that, you're done. Okay? Now, how can you prove that? Well, that's very easy, because you see this function as a continuous function of A3 does extend continuously to the boundaries. So let me put that explain that better. This is just a simple observation that the map A3 belonging to 1 infinity to R, given by this formula, extends continuously to 1 closed, infinity closed, and the extension maps why is it so? Well, just because the same formula is okay. When you replace A3 by 1, you just have the same formula, except that the exponent 1 minus lambda 2 and 1 minus lambda 3 are added. Now, if you think of what is 1 minus lambda 2, 1 minus lambda 2, this is the interior angle. 1 minus lambda 2 is the exterior angle. So it's very clear. If you have a quadrilateron, and if you move the sides parallel to each other until they meet, so here's a you see that the quadrilateron will degenerate in a triangle. So you have a family, a continuous family of quadrilaterons, which moves, and at the end becomes a triangle. And what is the angle of this triangle? This exterior angle of the triangle is the sum of the two exterior angles of the quadrilateron. So what I just mean is that when you take the Schwarz-Christoffel map, and when A3 is going to the boundaries of the domain, when A3 goes to 1 or to infinity, what is happening simply to the corresponding quadrilateron is that it degenerates to triangle. Okay? So just by continuity argument, you see that you can get any quadrilateron just by continuity argument. So this Schwarz-Christoffel map for quadrilateron degenerates to the Schwarz-Christoffel map for triangle when you go to the boundary of the domain. Is that okay? I see that Marco does not agree. Oh, I show you the two triangles. Yeah? So if you have a quadrilateron like that, it can degenerate this way, or it can degenerate this way. Okay? When you move A3, no, why? What do you mean? Well, everything is defined up to homothétie. So you have this. Really, you have this quadrilateron, and you look at the space of quadrilaterons having that fixed angles. That space. Yeah. So you are right. I should do this maybe L1 and L2, and L1 divided by L2. Something invariant under homothétie. So maybe I should not look at this L. What I just say is that the space of quadrilaterons with fixed angles is an open interval. And this open interval has two endpoints, and the two endpoints are the two triangles, which can be degeneracy of the quadrilateron. So, and if you have this quadrilateron, you can degenerate this way or this way. Okay? And what I mean, maybe I should not even write these formulas, is that the map given by Schwarz and Christoffel maps A3 to some quadrilateron. When I go to the boundary of A3, the quadrilateron will degenerate into one of the other triangles. So really, I have a map from the closed interval to a closed interval, mapping the endpoints to the endpoints. Therefore, it has to be onto. Okay, so maybe I should not even write this length or whatever. I just observe that the Gauss, the Schwarz-Christoffel map makes sense when AI is equal to AI plus 1. Okay? And degenerates to a Schwarz-Christoffel map of a triangle. Okay, so in general, you look at the Schwarz-Christoffel map, with n vertices, a n minus 1. You look at this map, and you look at this map as a function of A3, AN. Now, A3 is a real number which should be bigger than 1, less than A4, less than infinity. And now the simple observation is that even if I put equal here, then I have a well-defined map. If two consecutive AIs are equal, I have a well-defined map, which now is a conformal map not to an n-gon, but to an n minus 1 gon. So really what I get now, the space of n minus 1 tuples of real numbers satisfying that is a closed simplex. This is a closed n minus 1 closed n minus 1 simplex. Now I look at the space of polygons, the space, let's say, polygons with n sides and angles lambda 1, lambda n, modulo similarities. And exactly as before, this space can be compactified by adding to the boundary of it polygons with less sides, like n minus 1, n minus 2, etc. So this space can be compactified let's say polygon n bar And this compactification, again, is a simplex. Because if you want to describe a polygon up to similarity, you have to give the length of the sides up to multiplication, since you know the angles. So really, you have a simplex. So the space of polygons with given angles is also a simplex. And the Schwarz-Christoffel map is a map, a continuous map, from a simplex to a simplex. It maps an n-1 tuple of real numbers to a polygon. And this map does extend the boundary. And what we have to show is that this map is onto. You want to prove that any polygon is indeed obtained by some Schwarz-Christoffel map for some choice of the AIs. And we do by induction. We did that for triangles. We did that now for quadrilateral. And by induction, we have this family, this map, which on the boundary is onto. So you really have a map from a simplex to a simplex, sending the boundary of the simplex in an onto way on the boundary of the simplex, and hence it is onto by Brouwer theorem. Okay, if you have a map from a ball to a ball, which maps the boundary to the boundary, which on the boundary is a homeomorphism, this map has to be onto.
Is it one-to-one?
Oh, okay. It is one-to-one because I think you are not there. I showed in the previous lesson that if there is a conformal map, it has to be given by this formula. Okay? And, well, for the time being, I don't need one-to-one. But onto is okay. Huh? Okay. But you will see it's one-to-one. Okay, so really this is a proof by induction. You note that I use Brouwer theorem. And Brouwer was proved this theorem later than Poincaré. And there is an interesting letter from Brouwer to Poincaré, in which Brouwer complains that Poincaré is using this fact with no proof, that a map from a ball to a ball, which is, say, the identity on the boundary, has to be onto. That was completely obvious to Poincaré, and he gives no proof of that. And then Brouwer complains that this needs a proof, and the answer of Poincaré is really not nice. I mean, well, it's obvious. And then Brouwer gave a proof. The Brouwer theorem. Okay. So that was motivation for Brouwer. Okay, so really we have this, this is a typical example of continuity argument. We want to prove that a given object can be uniformized or conformally represented. We have a family of examples, and we show the map is onto by some continuity and looking at what's happening at infinity. Somehow we are showing that the map, the Schwarz-Christoffel map is a proper map. And in this case, how do we show it's proper? We show it's proper because it extends to infinity. And why does it extend to infinity? Because we understood infinity. And we said, we understood that the space, the space at infinity on the space of polygons is just polygons with one size less. Okay? Yeah. What? For non-convex, I don't know how to use this idea. That's a good question. Is true also for non-convex? I don't know. Okay, so that's the first example explaining the idea behind the continuity method. But again, it is not mentioned by Schwarz. It is not mentioned by Poincaré, by Klein. And to tell you the truth, this argument, I didn't see it anywhere in the literature. It should be classical, but does anybody has seen that somewhere? No? So maybe it could be a good idea to write it down in a clean way. Okay, so now let me go to a similar idea that led Poincaré to the following theorem. I told you it's August 8th, 1881. 82, sorry. Poincaré. And this I will explain that to you. It says the following. For any algebraic curve, of genus at least 2, there is a finite set f, x, such that the universal cover of the complement is Poincaré disk. Of course, we know that this theorem is true if you take the empty set. But at the time, Poincaré did not know that this could be true, and he was already satisfied by this uniformization of the complement of a finite set. So let me tell you the steps in the proof. The steps of the proof are the following. Step 1. I will show you that if you take the Riemann sphere and if you delete a finite number of points, but real points, then the universal cover of that is the disk. N bigger than 3. Of course, this is true if you delete points which are not real. But I will explain to you why it is easier to prove when the points are real. And this will be proved by continuity method. And then step 2 is a very simple exercise. It's the following. You take an algebraic curve x. So, of course, such an algebraic curve, let's say P of xy is equal to 0 in the complex projective plane, has at least a meromorphic function. For example, the function x. Function x is a meromorphic function on the curve. And the claim of Poincaré is this. You will take this meromorphic function and you will make it more complicated by composing here by some rational map. And the claim of Poincaré is there is a rational map G such that the composition has only real critical values. Has only real critical values. So said in another way, that means that you can delete to CP1 a finite set of real points such that away from this finite set of real points, you have no more critical points. So you will define F to be the inverse image of the critical points, critical values of G composes F. In this way, you get a map from your algebraic curve minus F to the Riemann sphere minus a certain number of real points. And now, since you know by step 1 that this object is covered by the disk, and since this map has no critical point, in other words, is a covering space, you can just pull back the cover by the disk that you have here. The disk covers this, so you just take the pullback here. And you get a covering space of X minus F by the disk.
Why n is bigger?
If it's not big, if it's 2, or just add more points.
Huh?
You add more points. You have the right to add points, as many points as you want. Okay, so if you have only 2 points here, you put third one. Okay? Okay, so then you're done. I mean, you have covered the complement of this finite set by the disk.
But
Okay?
you could find it covering like that, such that n equals
To 2.
equals to.
That's not possible, because then that would prove that X minus F is parabolic. Okay? Which is not the case. Okay, so let me, step number 2 is a very simple exercise. The exercise is this. This is really the exercise. Exercise. You know, when you want to compute the critical points, the critical values of G composes F, take derivative is G prime composes F prime. So the critical points, the critical values of G composes F is just the union of the critical values of F union the critical values of G. Am I right? Yes. Critical values. Sorry, it's G of Okay, so you know F and you're looking for G. And now the lemma or the exercise is the following. Given the finite set let's say S in CP1, there is rational map G such that G of S is real. This is easy. And the critical values of G are also real. So this is really a simple exercise in algebra. I give you a finite number of complex numbers, and your duty is to find a rational map that sends these complex numbers to real points. Easy. But you want to do that in such a way that this rational map that does the job of sending all points to the real points has only real critical values. Okay, so this you can do that if you. This is really a simple exercise. If you don't know how to do it, look on the compte-rendu note of Poincaré. This is a very unique case where he does everything like a good student with all details and all exercise. Really, this is an exercise. Okay, so really, again, you start with your algebraic curve. It has a rational map. This rational map has many critical points. Unfortunately, these critical points may not be real. So you compose by some other map to make them real without creating more non-real critical values. So you do that, and after that, you have a meromorphic function which is a covering space over the sphere minus a finite number of real points. And then by step one that I did not explain yet, you can pull back the universal cover to get a covering of the curve minus a finite set. Okay?
But why he asked if you
You will see that now, because of step one. If you take the complement of 4 points in the Riemann sphere, 4. Yeah, 3 you can assume real, and the 4th is somewhere. To prove that the universal cover of the complement of 4 points in the sphere is the disk is not obvious at all. How do you do?
Uniformization.
Yeah. So that's not obvious at all. You have 4 points in the sphere. Proving that the universal cover of the complement is the disk is not obvious. What is easy, and I'll show it to you now, if the 4 points are real, you will see that. If the 4 points are real, easy. Okay? Now, I think, but I'm not sure. Maybe this is not exercise, this is question. Maybe I think it's easy. you can always assume that n is equal to 4. I think. You cannot assume n is equal to 3. Is that clear? It is a well-known theorem in algebraic geometry that if you have a Riemann surface, and if this Riemann surface has a meromorphic function with only 3 critical values, this algebraic curve is very special. It has to be an algebraic curve defined over the algebraic numbers. In particular, this is the Bayes' theorem. In particular, only a countable number of Riemann surfaces have the property of having some meromorphic function with 3 critical values. What I think, I was trying to do that this morning, I couldn't do it, but I think it's probably easy to show that any Riemann surface has a meromorphic function with 4 critical values, and you can even assume that these 4 critical values are 4 real numbers. But that's maybe true, but probably useless. Okay, so let me go to step 1. And this is explicitly well explained in the compte-rendu note of August 8, 1882. So you can see that in August, Poincaré was not taking vacation. Huh? Okay, so I want to take, let's begin by 4 points. I take CP1 minus 4 points. Real points. So I can assume this is 0, this is 1, this is infinity, and this is x. And I can assume x is between 1 and 0. And I want to show, Poincaré wants to show that the universal cover of that is the disk. Now what he knows, and this is what I explained last time, he knows how to construct examples of Fuchsian groups. We have seen Monday that, for example, if you take an ideal quadrilateron on the disk, limited by 4 geodesics, let's say this is 0, 1, infinity, and this is lambda. Well, Monday I was gluing this and this by some isometry, and this with some isometry, and I explained to you that this creates a discrete group, but there was the problem that maybe the discrete group did not have this as fundamental domain. But today let me do this way. I identify this with this, and this with this by some isometry. Of course, the isometry sending this to this is not unique. And we have the same problem that we had last time, that if we choose an isometry at random, probably will not create a sphere minus 3 points. Topologically, if I identify this and this, this and this, I create topologically a sphere minus 4 points. 4 points or? Three points. 3 or 4? Sorry. Is used what? Of what? Yes, yeah, but okay. So let me put it this way. Take such a quadrilateral, and now play the game of using symmetries with respect to the sides. So you will create in this way a Fuchsian group whose fundamental domain will contain two copies of that. Because you have the symmetry. Okay? And if you take the quotient of the Poincaré disk by this Fuchsian group, you get a sphere with 4 points deleted. You know, this is the group generated by symmetries which are not holomorphic but anti-holomorphic. Okay? Inversions, if you wish. Okay? So you take the symmetry with respect to the sides. So this is a group which is acting on the disk by isometries, which has a subgroup of index 2 consisting of holomorphic transformation. And if you look at the fundamental domain, you need to use two of them because one is the symmetry of the other. Okay? And then the corresponding quotient will be a sphere minus 4 points. Because you have one vertex here, one vertex here, one here, and one here. Okay? So this is identified with this. This is identified with itself. This is identified with this, and this is identified with itself. So you have 4 points are missing in the sphere. Now, is it clear to you that the 4 points that we get on the sphere are real? If we play this game, you construct 4 points on the sphere. And the observation is that the sphere, the 4 points are real, of course, up to Möbius transformation. Or if you want, instead of saying they are real, they are cocyclic. So why is it so? This is something that really Klein did not understand at first. When you take a polygon in the Poincaré disk, and if you play the game of taking symmetries and symmetries and symmetries, what you produce in this way is the Riemann surface, which is very special. It has some anti-holomorphic involution coming from the symmetry. So if you play the game of taking a polygon and taking symmetries and symmetries and symmetries, and if you assume that the angles here are of the form pi over k, you do construct some examples of Riemann surfaces. But these Riemann surfaces are very special. They have an anti-holomorphic involution. And most Riemann surfaces have no anti-holomorphic involutions. Today, in order to thank Felix Klein, people call a Klein surface to be a Riemann surface with an anti-holomorphic involution. And here, of course, there is an anti-holomorphic involution coming precisely from this symmetry. So if you play this game, we get the sphere minus 4 points, but this sphere minus 4 points is not any sphere minus 4 points. It is a sphere minus 4 points which has the property that it is invariant under some anti-holomorphic involution. Anti-holomorphic involution of the Riemann sphere up to conjugacy is just z goes to z bar. So the 4 points that we create in this way, up to conjugacy, are on the same line. They are real numbers. So this construction of taking a quadrilateron and taking symmetries and symmetries and symmetries, you can do whatever you want. You will not create 4 points which are not real. This is it. If you want to prove that the universal cover of complement of 4 points on the sphere is the disk, if the 4 points are not on the same line, you need another idea. These ideas of taking a polygon and playing the game with symmetries will not work. But maybe for real points it will work. And this is indeed what is happening. Now, for 4 points, we take, so we have 0, infinity, 1. And here we have a free parameter, x. So let me call it lambda, it's better. Or to be consistent, let me call it a. And so for each value of a between 0 and 1, I play the game of symmetries, etc., etc., and this constructs for me 4 points on the sphere. These 4 points, I can call them on the line. I can call them 0, 1, infinity, and the fourth, I can call it L of A. The fourth point is a function of A. And so this gives a function, L, from 0, 1 to 0, 1. And the trick of Poincaré, of course, is to say, well, this function is onto, and the way to show it's onto is to show it extends to 0 and 1. Continuously. And this is what he does. So, just like we had for the Schwarz-Christoffel construction, we have a quadrilateron here with one free parameter. This free real parameter provides 4 points in the sphere on the real axis. 3 of them are fixed as 0, 1, infinity. And the fourth one is also a free number. So you just adapt the A. You adapt the A to get any x. This is the second example of the continuity method. What? L is not equal to A. No, it's terrible, complicated function. L of A is something like Schwarz-Christoffel formula. It's a transcendental function. It is monotonic, but it's definitely not the identity. It's something, you are going. Uniformization is a transcendental procedure. When you go from there to there, it's given by terrible, complicated transcendental functions. Solutions of hypergeometric equations, etc., etc. So it is definitely not the identity. Just like in the case of Schwarz-Christoffel. Now what Poincaré does is that what's happening now if you want to realize endpoints on the real line. Well, you do exactly the same thing. You take now a polygon. Take its reflections. And this is the same game. But now, instead of, you can fix 0, 1, infinity. And now the three parameters are the A1, A2, AN. And we have exactly the same situation that we had in the case of Schwarz-Christoffel. For each choice of A1 less than A2 less than AN, maybe it's the wrong order. For each choice of real numbers, you have a polygon, you identify it, you get a sphere minus a certain number of points on the same line. And we want to show that you can adapt the values of AIs to reach any choice of the XIs. So, of course, this is 1 infinity. And the functions x4, xn are functions of and this is the same thing. You have a map from an n-dimensional space to an n-dimensional space. You want to show it's onto. And the trick is the same. You show this map extends to a natural compactification. And the natural compactification, just very easy, just collapsing two of the AIs. And you get by induction that the map you want to prove it's onto extends to the compactification. And again, using some form of Brouwer theorem, you prove the map is onto. And that gives the outline of the proof of the weak form of uniformization theorem. If you delete a finite set of points in an algebraic curve, the universal cover of the complement is the Poincaré disk. Okay, so now that we have that, let me begin the general construction that came out of Klein and Poincaré later on, without deleting a finite number of points. So I choose a surface of genus G and call gamma its fundamental group. Note that at the time there was no fundamental group, because the fundamental group was invented 10 years later. But nevertheless, in this case, Poincaré had a very clear idea of what is the fundamental group. And we are going to consider two spaces. The space number one is what we call today Teichmüller space. Which is the space of Fuchsian groups isomorphic to gamma. So it's a space of embeddings of PSL in PSL2R with a discrete image and such that the quotient of the disk by gamma is homeomorphic to the surface. And this, I will take the quotient by up to conjugacy. In PSL2R. So this is the space of Fuchsian groups of a given genus. And the second space will be the let me call the Riemann space, genus G. This is the space of the set of complex structures on the surface of genus G modulo isomorphisms homotopic to the identity. It is not empty because last time I showed you how to construct examples. We have many examples. Okay? Okay, so let me say a few words about these two spaces. Let me begin by the second one. Riemann, for the second, proved, in quotes, that this is a complex manifold of dimension 3G minus 3. All right, I will not explain exactly how he did it, but I just want to give you a few hints of how he was thinking and why it was somehow clear to him that we need 3G minus 3 parameters. Here's the way Riemann was thinking. You take a curve of genus G, and you assume you have a complex structure. So it's a Riemann surface. Then Riemann had proved that on this Riemann surface, the space of holomorphic one-forms has dimension G. The space of so-called abelian differentials, holomorphic one-forms, has dimension G. So he proved it. Now, how to construct invariants out of that? He said, well, let us choose on the surface G curves like 1, 2, and 3. Curve gamma 1, gamma 2, gamma G. This is the way he was cutting the surface along these closed curves. And he said, well, I have G forms, a space of dimension G. I have G curves. I can select the unique the unique one form which has a given set of value of integrals over gamma 1, gamma 2, gamma G. So there is a unique form omega, which is holomorphic, and whose integrals over the gamma i's is given. Okay, so that selects a specific holomorphic form on the Riemann surface. This selection, of course, depends on the choice of these curves gamma I. So you need really a marking of the fundamental group. Now what can you do with this unique form? Well, as you know, the H1, and as Riemann knew, of course, the H1 of the surface of genus G is 2G dimensional. So this unique form, we know its periods over gamma 1, gamma 2, gamma G, but we don't know its periods over the alpha 1, alpha 2, alpha G. So this unique form, you can integrate it over the G curves which are missing in homology. So this unique form will give you G numbers. You get G numbers, complex numbers, which are just the integral of this unique form on these alpha i's. So any complex structure on the Riemann surface gives you numbers. The integrals of this unique form on these curves. But these numbers are not enough to characterize the curve. You miss more numbers. And what Riemann says is that any holomorphic form on the surface vanishes at some points. And we know in how many points. It vanishes in exactly 2G minus 2 points. So on the surface, you have 2G minus 2 points on which this unique form vanishes. Okay? So you choose one of them. And you integrate this unique form to the other ones on some path. And you get 2G minus 3 very complex numbers. So they are the integrals of this omega from this base point to the other zeros of omega. And in this way you get 2G minus 3 complex numbers. So this is just a recipe. I give you a Riemann surface. I give you some homotopy classes. And with that, you construct 3G minus 3 complex numbers. 2G minus 3 coming from the integrals between two zeros of omega, and G coming from the periods of this omega on the missing curves. So Riemann explains that, and then he explains that these 3G minus 3 complex numbers are really enough to describe completely the complex structure, at least in the neighborhood of the given one. And this is rather convincing. And this is proof. So really when I say Riemann proved that this is a complex manifold of dimension 3G minus 3, I think it's indeed rather convincing. He really found local coordinates for this space. These local coordinates are really given explicitly by integrals of, you can compute numbers. It really gives local coordinates on this space. It never proved it's a contractible space or whatever. It never proved it's a ball, as we know today. But he did prove that this is a complex manifold of dimension 3g minus 3. So this, I think it's convincing. Now, concerning that, we will discuss that next time. But now I want to show you the main part of the continuity principle is this. We have a map, Teichmüller space of G, to Riemann space. And this map is really analogous to the Schwarz-Christoffel map. On the left-hand side, we have groups, we have polygons, we have Fuchsian groups. On the right-hand side, we have transcendental objects. I mean, we have Riemann surfaces. Like we had the sphere minus 4 points, for example. And this map is tautological. You take a group, take an element here, it's a group acting on the disk, and the quotient is the surface. The surface is a Riemann surface. So any object here gives you canonically a complex structure on the surface. So this map is completely canonical. It just associates to each group the corresponding Riemann surface. And the goal is to show this map is one-to-one. And we will use ideas similar to the ideas that we had in the two examples. Examples of polygon, examples of endpoints on the real line. I will not do it now. Let me show it just that easy part. It is one. It is, when I say one-to-one, I mean it's bijective. And the only thing I want to show you now, it's called the lemma phi is injective. So the proof is just two lines. Is Schwarz lemma. Actually, in the paper of Poincaré, Poincaré expresses this property of being injective very explicitly. He mentions this is the important point. And for the proof, he mentions Schwarz. This is the only place in Poincaré where I've seen a explicit mention of Schwarz. And why is it so? Well, what does that mean that 2 points here have the same image? Well, that would mean that you have two groups leading to the same Riemann surface. So that would mean that you would have two quotients, two homomorphisms, gamma embedding in two ways in PSL2R. Let's say I1 and I2, and such that the disk minus divided by I1 of gamma, and the disk divided by I2 of gamma would be holomorphically isomorphic, biholomorphic. And moreover, they would be biholomorphic by something homotopic to the identity. So that would mean that there would be a holomorphic map let's say U, from the disk to the disk, which would be conjugate the two actions. But we know by Schwarz lemma that the only biholomorphisms of the disk are elements of PSL2R. So this U that a priori is only supposed to be holomorphic, a posteriori is in PSL2R. And so this conjugacy turns out to be a conjugacy inside PSL2R, which means that I1 and I2 are the same points in Teichmüller space. So injectivity from the Teichmüller space to the Riemann space is just a simple consequence of Schwarz lemma. Okay? Now, surjectivity will amount to show properness of this map, and this will be what I'll try to do next time. Okay? So let me stop here, just a few words. Mistake, one of the mistakes that Poincaré makes, and that Klein makes also, he claims that injectivity of this map, which is correct, seems to imply for him injectivity of the differential of this map. And he uses it many times. And to tell you the truth, I'm not sure. I don't know if it's true, actually. So you have this. We would need some kind of infinitesimal Schwarz lemma, but I don't know how to prove it. So we will do something else. I mean, because the point was, at the time, Poincaré was not aware of the invariance of domain. He didn't know that an injective map, an injective open map from Rn to Rn is a local homeomorphism. If you assume it's a smooth open map, and if you assume the differential is 1-to-1, then you can use the inverse mapping theorem to get it's an open. Anyway, so we will see that we will try to not to use that. Anyway, I don't know if it's a locally if the differential is injective. Okay, we are still a long way from the uniformization theorem, but I hope at least the strategy is clear. It started from polygons, then you try to move things to adapt the right side. Why?
Because Teichmüller space is smooth and the other one is not.
It is. This is not the moduli space. No, it is the what? Teichmüller. This is a smooth one. Homotopic to identity. No. This is really a smooth, complex manifold, which actually is it's completely smooth object. This is also a smooth object. We understand very well tangent space in both sides. Yes, both are different ways of thinking Teichmüller space. Today we mix the two of them because we know uniformization theorem. But it's good to distinguish them. This is why I didn't call it the Teichmüller space here, because we know they are the same, but because of this theorem. Okay? Okay, thank you. Where? Ici.